Why curved arrows in the first example are absolutely horrible, while the curved arrows in the second example are actually good. If you're confused about that, let's talk about it right now. Hello everyone, Victor is here, and in this video I'm going to talk about how we use curved arrows in organic chemistry. There are three main scenarios how we are going to be using curved arrows in organic chemistry. First one is going to be in resonance, and we have already talked about resonance before and how to move electrons between the different resonance contributors. The other two, acid-base chemistry and reactions in general, they're going to be showing the movement of electron density between the molecules, showing how the electrons move, giving you different products of the reaction. And before we jump into the discussion of the curved arrows themselves, we need to talk about the anatomy of the curved arrow, so to speak. So whenever we show the curved arrow has two distinct places. We have a place from where the electrons originate, which is going to be our source of electron density, and we're also going to have a place where electrons are going, which we're going to refer to as electron sink. The beginning of the arrow, this place, is what we are going to refer to as a tail, while the part with an arrow, that is our head. And electrons originate where the tail is and they go to where the head is pointing. So typically we are going to be seeing our electrons are being either a bond between two elements, let's say some sort of element X and Y, or they can be an electron pair on the element itself, so let's say on an element X. So if I'm showing a curved arrow like this, that means that the electrons are going from the bond between the element X and Y somewhere else. If I'm showing the curved arrow like that, it means that the electrons are starting on my element X, the electron pair on the element X, and those electrons are going somewhere else. So here is an example of a reaction. In this case, in order to move my proton, this proton over here, from HCl onto H2O, giving me H3O, what I need to do, I will take the electron pair from the oxygen and I will give those electrons to the hydrogen. I will share those electrons with my hydrogen, while at the same time, hydrogen cannot accept those electrons without giving away some of its electron density. So I'm going to move some of the electron density between the hydrogen and chlorine onto the chlorine. Now, chlorine used to have 1, 2, 3 electron pairs on it to begin with. Those 3 electron pairs are still on my chlorine on the right side. However, the bond, which used to be between my hydrogen and chlorine, now is an electron pair on the chlorine atom. Likewise, the electrons which used to be an electron pair on the oxygen are now going to be a bond between oxygen and hydrogen. So remember, whenever you are pushing electrons onto something, that something must be able to accept those electrons, or if that something does not have a place for the electrons, then that new element has to break a bond and let something go. For instance, let's take a methoxide anion over here. If I take the electron pair from the oxygen and try to push it onto the carbon, what I'm going to end up with is going to be a carbon which still has all of its hydrogens, but now I'm pushing electrons to make a carbon-oxygen double bond like this, which would be a big problem because now my carbon exceeds its octet, it has 10 electrons around it, and it is physically impossible, which means that doing something like that is going to be a bad arrow pushing. We cannot do something like that. On the other hand, if let's say I have a species where the carbon has an empty orbital that is a carbocation, and I'm trying to do exactly the same thing with my oxygen pushing electrons onto a carbocation, well, in this case now I'm going to end up with a carbon with a double bond to the oxygen like this, and now I do not have any problems with my carbon having too many electrons. It does have a full octet because before it only had 6 electrons around it, and before it had an open shell. Now we have a closed shell. So in this case, that is a good curved arrow. So whenever you're pushing electrons onto something, that something, as I mentioned a moment ago, needs to be able to accept those or it will have to break a bond. And since I'm talking about the possibilities of breaking bonds, here is another example. Let's say I have a similar molecule to what I had before, but now instead of one of the hydrogens, I have a chlorine and I still have an oxygen atom nearby with excessive electron density. In this case, if I just push the electron density onto carbon, I will end up with the same problem as before, where my carbon will have too many electrons around it. So if I redraw everything there, I will have carbon with 10 electrons around it, which is absolutely horrible. We cannot do that. So that would not be possible. However, if I take exactly the same molecule, and I'm going to redraw it here real quick, so I have my chlorine, I have my hydrogen, and I have oxygen with all of its electron pairs like that. So if now I were to, for instance, push electrons onto the carbon, and at the same time carbon will break the bond with the chlorine, then what I'm going to end up with is going to be a carbon which is double bonded to oxygen, and on top of that we have a chlorine atom which now is floating by itself with a negative charge. And I will remind you that chlorine used to have 3 electron pairs around it to begin with, so those electron pairs are still there, and the bond, which used to be between my carbon and chlorine, now is an electron pair on chlorine atom like that. So in this case, my curved arrows are good, and I have no problems with this curved arrow formalism here. Now, whenever we have electrons being pushed onto the atom with a full octet, we don't always have to break the last sigma bond. Sometimes we can push the pi bond away. So, for instance, in the case that I have here on the screen, what I can do, I can take an electron pair from my oxygen and I can attack the carbon. If I'm attacking that carbon, I'm going to highlight that carbon in green. So if I'm going to attack that green carbon, it won't be able to accept electrons because currently this carbon already has a full octet. So in order to accept those electrons, the easiest thing that the carbon can do is just to push the pi electrons away onto the oxygen. So in this case, what I'm going to end up with is a molecule where I have an oxygen carbon making a new bond, so the electron pair that I took from the oxygen to share with the carbon, now that electron pair is making a bond between my oxygen and the carbon, and the pi electrons, let's highlight those in green, so these pi electrons are now an electron pair on my oxygen atom. So that is an example of how we use curved arrows between the molecules to describe the electron flow in our reaction. Remember that whenever we are doing reaction in organic chemistry and we're showing our curved arrows, we're always going to be showing the movement of electrons rather than movement atoms. Atoms will follow the electrons, so never show where the atoms go, always show where the electrons go. So to make your life a little bit easier when it comes to curved arrows, always remember a few important tips. First, always start your curved arrow from a bond or an electron pair on an atom. Never show your curved arrow starting from a positive charge. Point your curved arrow to where the electrons are going. Either they're going to be going back to an atom or they're going to be making a new bond between the atoms. And never use your curved arrows to show the atom movement. It's always all about the electrons and never about atoms. And of course, practice makes it perfect, so make sure that you are practicing your curved arrows to be comfortable with those so you can use them for resonance and reactions as well. Go to organicchemistrytutor.com for more practice tips and tutorials on different topics, and of course, any feedback, questions and comments, leave them in the comments below, and I will see you in the next video.